Okay, welcome back, everybody. So our first speaker this morning is Draisma, who will speak on the geometry of GL-Varieties.
Okay. Thank you very much. Thanks to the organizers for the opportunity to speak here. It's a pleasure to be here also in this time of the year. I've been enjoying the smell of the honeysuckle outside. So my talk is about certain varieties that are not Noetherian, but they become Noetherian when regarded up to the action of a big group. This is a research theme that has been recurring in my own research over the last years and also in that of other people. And usually it's one of two groups that play the role of the large group. Sometimes it's the infinite symmetric group, and sometimes it's the infinite general linear group. If you're interested in questions about the infinite symmetric group, I'll be happy to talk to you afterwards. But in this talk, it's the infinite general linear group that plays a role. So the setting is the following. I'm going to work over an algebraically closed field, basically for simplicity. And I'm going to assume that the characteristic is 0. And this seems to be really a necessary assumption, at least for some of the statements. We don't really understand yet how the theory looks like in positive characteristic. Well, what is GL? So GL is just, it's the union over all n of GLN. And so you think of GLN as sitting inside GLN plus 1 by appending a 1 here and zeros here and zeros here. So it's the standard infinite general linear group. And so you can think of the elements as infinite by infinite matrices that in all but finitely many of the positions agree with the identity matrix and that are invertible in there. Okay, so that's the group. V is going to be the standard module for this. So it's just a countable dimensional vector space over K with bases E1, E2, and so on. And GL acts on it in the natural way. So now, the algebras that we're going to work with, they are also representations of this infinite general linear group, and they arise from V essentially by taking symmetric algebras of tensor products or direct sums of tensor products of V. So let me be a little bit more precise. So if you have a GL module over K, then it is called polynomial if it is contained in some direct sum, and this can be an infinite direct sum of tensor powers of DI, tensor powers of V with exponents that can vary. So this is what's called a polynomial GL module. And so the algebras that we're going to study are going to be such polynomial GL modules together with an algebra structure that is compatible with this GL structure. So a GL algebra, so I guess that's our first definition. A GL algebra is a polynomial GL module with a compatible commutative unital K algebra structure. And so by compatible, I just mean that the multiplication is a homomorphism of GL modules from the tensor product of the algebra with itself into the algebra. Okay, so it's a algebra object in the category of polynomial GL modules.
I think of GL as just being an abstract group.
Sorry, oh, that's a good question. So yeah, so GL is actually, it's an int group. It's a direct limit of algebraic groups, but that structure actually doesn't really play a role in anything I'll say. Yeah. Yes, but that's right. But if things are polynomial, then it is also going to be a homomorphism of int. I mean, then it's also compatible with the int group structure. So I will not have to say int group, but it's kind of implicit in the whole story. And so there's a natural notion of finite generatedness. So such a GL algebra, let me call it R, is finitely generated if, well, if it is generated as an algebra by some finite length GL submodule. So, in fact, we understand very well what are the polynomial GL modules. They are direct sums of sure modules. So any polynomial GL module is of the form some direct sum of S lambda V, where S lambda V, well, first of all, lambda is a partition, let's say, of some integer D, and S lambda V is just, let me see if I get this right, it's the homomorphisms of SD modules from U lambda to V to the tensor D. So SD is the symmetric group on D letters that permutes the tensor factors here, and U lambda is the irreducible representation of this SD corresponding to the partition lambda. So any GL module has such a decomposition, and then the condition of finitely generated is just that that you can choose finitely many of these, and they generate the thing as an algebra. And so let me just give one example that I'll try to return to throughout the talk. It's kind of one of the easiest examples you can think of. R0 is going to be the symmetric algebra of V tensor V. Okay. Yeah, I'm saying this is semi-simple. Yes, that's right. So that's one of the things that become more difficult in positive characteristic. Yeah, so this is isomorphic to the infinite polynomial ring in variables y, I, j, where I and j run through the natural numbers. And yeah, just you send EI tensor EJ to EJ to Yij, and you can figure out how the infinite general linear group acts in this model of this algebra. And it is essentially, let me get this right. I think if you want to if you want to apply an element of the infinite general linear group to YJL, then you get the JL entry of, put this up. Yeah, that's right. Yeah, there should be parentheses here. I'm not going to slide it down, but that's right, yeah. Thanks. So it's the GL entry of G transposed times Y times G, where Y is an infinite by infinite matrix of variables, and this is how you left and right multiply with an element of GL. And so now there is already a fundamental question that we do not know the answer to, namely, is every finitely generated GL algebra Noetherian? Yeah, so this let's ask if you have a chain of ideals, let's say I1 and I2 and so on. And yes, exactly. So GL stable ideals. Yeah, that's right. So maybe it would be wise to put here GL Noetherian, right? Because we all agree that algebra over there is not Noetherian in the classical sense, but is it true that if you have GL stable ideals, then IN is equal to IN plus 1 for all n sufficiently large? We do not know the answer to this question, and in fact, we do not even know it in this particular example. So it's a little bit surprising. There are some positive results, namely in cases where you understand completely the module structure of a GL algebra, and where it is, for instance, if it is multiplicity free, that all the representations in there appear only once, and then it becomes a kind of a combinatorial game to understand ideals in there. And in those cases, we know that this is true. So it is true for the symmetric algebra of S2 of V. Let me put the brackets correctly now. So that's just the symmetric square. And it is also true for the symmetric algebra of wedge 2 of V. And there are some other cases. And this is all work by Nakpal, Sam, and Snowden. Sorry, what's that? Oh, yeah, thanks. Yes, of course. Yeah, I should have started with that. The symmetric algebra of V itself is also Noetherian. And in fact, this is the only one among them that is already Noetherian under the infinite symmetric group. So, so that the other ones are too big for that. Yeah, that's the thing. And in fact, I haven't quite done justice to their work yet. These statements about these algebras being Noetherian is fairly easy, but they prove something much stronger, namely that finitely generated modules over this algebra with a compatible GL action are also Noetherian. So that's a much stronger statement. Okay, but already in this example over here, we do not know whether this is the case. And fortunately, we do know that something weaker than this holds, namely at the level of topological spaces, such a statement is true. And that brings me to the topic of these GL varieties in the title of my talk. So let's say definition is a GL variety is the spectrum of a finitely generated and reduced GL algebra. So, so what are examples of this? Well, of course, we have an example over there. So the spectrum of R0 is just the space of infinite by infinite matrices. We call it n by n matrices. And there are many other examples. Well, in fact, let me give another example over here. So if I look at X inside this guy, so the spec of R0 defined by all 3x3 subdeterminants. Yeah, that's the space. That's the variety of infinite by infinite matrices of rank 2. That is also an example of a GL variety. Now, just like affine varieties always live in some affine space, the same holds for GL varieties. And so, in fact, every finitely generated GL algebra is a quotient of some algebra that looks like this. Yeah, you take oh, sorry. I think I was writing this as a subscript. You take a direct sum of Schur modules, Schur functors applied to V, and you take the symmetric algebra of that. And then that means that dually any GL variety sits inside something that we call A lambda with a bar under it. So this lambda with a bar is just a tuple of partitions lambda 1 up to lambda r, and this is just the product of the spectra of well, the symmetric algebra of this and the symmetric algebra of this one, and so on. Yeah. So let me do an explicit example over here. So here spec R0 itself is in fact equal to A to the 1, 1 and 2. Yeah, so this is the partition that corresponds to skew symmetric matrices, and this is the partition that corresponds to symmetric matrices. Just for fun, yeah. I'll get back to this example eventually to illustrate something about the structure of GL varieties. And, but yeah, you can put anything there. And in fact, there are much more complicated ones. For instance, you can put rank conditions on the symmetric part and on the skew symmetric part independently, or also say something about the relation between the symmetric and the skew symmetric part of your matrix. That would work, yeah, that would just be the 0 point then. That's only 1 point. It's just the origin. So it doesn't really, so you can think just prime ideals. Sure. Yeah. Okay, but in the same way, A to the n is not the space of n tuples. I agree, but so one of the features of GL varieties that maybe I'll mention is that that like for affine varieties, k points are dense in them, and so it doesn't make much difference how you think about them. But yeah. Okay. Okay, so this is, let me see. At some point I knew I was going to forget how this goes. This one should go up. No, this one should go up. Yeah. Opla. So, so these are strange spaces. For instance, if you take such an A lambda, let me give a concrete example of that. So in particular, if you look at A and you have just a single partition corresponding to D, the number D, then this is then you can think of this as the affine space of degree D forms on V. Yeah, so a typical K point of that would look like you take some sum, and it's an infinite sum, ID, and then CI1 up to ID, and then XI1 up to XID. So that would be a typical point, K point in this space, if these are numbers in K. And so if D is bigger than 0, then there's always a dense orbit for GL in this space. And in fact, there are many dense orbits. There's uncountably many dense orbits in this space. So it's a little bit pathological space to think about when you're used to finite dimensional spaces with an algebraic group acting on them. On the other hand, you can introduce an equivalence relation which says that 2 points are equivalent if their orbit closures are the same. And under that equivalence relation, well, there's a lot more structure to this space. Okay? I don't want to go too much into detail there. Yeah, so for instance, if D is equal to 4, then just the sum of x1 to the 4 and x2 to the 4 and so on, that would be such an element with a dense orbit in this space. Okay, so now the starting point of this geometry of GL varieties is that they are Noetherian. So any chain say if you start with an A lambda and then you have a chain of GL, of closed GL subvarieties, GL subvarieties stabilizes. Right, so what that means in terms of the question that I asked up there is, well, we do not know whether every ideal is, GL stable ideal is generated by finitely many orbits under GL, but we do know that it has the same radical as some ideal that is generated by finitely many GL orbits. Okay. Now, so once you have Noetherianity, you can try to use this to translate other statements about finite dimensional affine varieties into statements about GL varieties. And we have been reasonably successful in this. For instance, there's a version of Chevalley's theorem, which says that if you have well, maybe let me just write it down. So it's Chevalley's theorem about constructible sets, which in the classical setting says that the image of a constructible set under a morphism is again constructible, and the same holds here. So if phi from x to y is a GL equivariant morphism of GL varieties, and well, let me say it like this. So let's say C contained in X is locally closed, by which I just mean open in its closure, and GL stable, then phi of C is a finite union of such objects. So that's a version, more or less an exact analog of Chevalley's theorem from the finite dimensional setting. And so this theorem and also some other results that I mention later, they are fairly easy once you have this Noetherianity result, or once you know the techniques that go into the proof of this. But today I'd like to present a bit of work with Arthur Bick and Rob Egermond and Andrew Snowden. And in fact, it is fair to say that all of the clever ideas, almost all of the clever ideas in this theorem are due to Andrew Snowden, which is about essentially about connecting points in GL varieties by means of curves. So sorry, what's that?
It's gonna GL variety out.
Well, so it is Noetherian. So it has finite. So it is a finite union of irreducible components. And yeah. So I would say just finitely many. It's just what you can have is what there are many of is what we call GL generic K points, and they are points that are dense in well, okay. That are dense in an irreducible component, whose orbit is dense in an irreducible component. Sorry. Well, okay, sorry. Maybe I didn't answer your question. So I guess it depends. So so the question is, what should if it's about let me check. Exactly, that's the question. What's the generic one? Yeah, I think so just minimal prime ideals, right? Yeah, I think just those finitely many that correspond to the irreducible components. I think that's just it. Yeah, and I guess that is the place where you need to use the fact that GL is also an algebraic group, right? So every GLN is a connected algebraic group. So every finite GLN acts must preserve irreducible components, and hence also the whole group. We don't need to assume that. For which statement do you want to assume?
Dense orbit.
No, you don't need to assume that. No, because just if you just think about a tensor product, then you can just you know, take independent vectors and take their tensor product, and then plus a similar thing with other independent vectors and so on. That gives you a point with a dense orbit. So you don't need difficult coefficients. In some of our work, at first it was useful to think about large fields, but then in hindsight, it wasn't really necessary. And so the theorem that I'd like to say a bit about says, so this is with the three other people that I mentioned, let phi from x to y be a GL equivariant morphism between GL varieties, and let x0 in be in the closure of phi, and let me take a k point of that. Okay, so so it's a k point in the closure of the image of phi. Then there exists a bounded k double brackets t point. I'll say in a moment what I mean, of y, such that the limit for t to 0 of phi of yt, oh, I guess that point is called yt, is equal to x0. And so, so what I mean is that, well, if you think about y sitting inside one of these affine spaces, a to the lambda, then it has countably many coordinates. And what I want is a point in which all those coordinates are Laurent series in T with coefficients from K, but with a uniform lower bound on all the negative exponents of T. So a uniform lower bound on the exponents of T. Sorry, what's that?
Why an X flipped in the map?
Oh, yeah, sorry. Yeah, I guess yeah, sorry. It's a map from Y to X, thanks. Right, so bounded means that, that there's a uniform lower bound on the exponents of T that appear in any of the coefficients of Y. And this just means the usual thing that, well, if you substitute y in phi, then all the negative exponents of t, their coefficients cancel out, and the constant part is equal to x0. Okay, that's what this theorem says. Now, this is of course, again, an exact analog of a theorem in finite dimensional algebraic geometry. See if I do this. And before saying a little bit about what goes into the proof of this theorem, I'd like to discuss an application to the strength of polynomials. So let me just say this in the finite dimensional setting. If you have a polynomial in n variables, then this has strength, or also Schmidt rank at most R, if you can write it as a sum of R terms. Well, I want to assume that it is a homogeneous polynomial of degree D, where Fi and Hi all have degree degree smaller than d. Okay, so a linear form has infinite strength if it's non-zero, but from degree 2 on, there's always such a finite r, and the smallest r for which you can do this is called the strength. And of course, you may assume that these are homogeneous and their degrees add up to d. No, d, you should think of d as being some fixed number, and r is the number of terms in this expression. Yeah, sorry, that's an r. Okay, so let me say a little bit, give you a bit of a feeling for what this means. So if d is equal to 2, then the strength of f is just equal to roughly a half times the rank of f, I mean, of the corresponding symmetric matrix, and then you have to round upwards. Yeah, it's just, well, x times y has rank 2, but strength 1. And in particular, in this case, being of some bounded strength is a closed condition because it's given by determinantal equations. So, so strength less than or equal to r is closed. Now, let's go to degree 3. And so for degree 3, actually strength has a very nice geometric interpretation. So for d is equal to 3, the strength at most r means that f vanishes on a codimension at most r linear subspace. Right, because if you look at that decomposition, the degrees of, without loss of generality, the degrees of the fi's are equal to 1, and those of the hi's are equal to 2. And then the space where the fi's vanish, their f vanishes. And this, and that's an if and only if. And this is clearly also a closed condition. So strength at most r is also closed here. Yeah, that's well, the f that I started with was homogeneous. They are without loss of generality homogeneous because you can just look at the parts whose degrees add up to 3 or to d. Well, they have to have, let me see. You're saying you could have, yeah, maybe I want to say that their sum of the degrees is, let me say they're homogeneous. I think you're right. Yeah. Yeah. Okay. Let's say they are homogeneous too. Okay. That is certainly what I meant. I just had in my mind that I didn't need to assume that, but maybe I do. So, okay. Anyway, now for d is equal to 4, the situation is more complicated. And then there's a paper by Eduardo Ballico and Arthur Bick and Alessandro Oneto and Emanuele Ventura that says that the strength is not strength at most 4 is not a closed set. And what they do, so let me sketch a little bit how this works. What they do is they show that if you have, where is it? If you have x, y, u, and v, which are linear forms, and f, g, and p, and q, and they are quadratic forms, then x squared times f plus y squared times g plus u squared times p plus v squared times q is a limit for t going to 0 of a sum of products of, well, a sum of 3 things. So let me write down one of the terms, and then I won't write down the whole expression, but you can, it's a kind of puzzle to fill it out yourself. So it's x squared plus t times g, and then multiplied by y squared. No, I think I want to put a t inverse y squared plus f here. And then there are 2 more such terms. And so what you see here is that you have something, you have a sum of products of quadratic forms depending on the parameter t. And if you add them all up, then the negative exponents of t cancel out. And for t equal to 0, you get precisely, I mean, yeah, for the constant term is precisely this expression over here, which has 4 terms. And then they argue that that provided that the number of variables is large enough, and they cannot say how large, but provided that the number of variables is large enough, then this expression over here really has strength 4 rather than 3. Okay, so that's how this argument works. Okay. That's right. Yeah. Yeah, sorry, 3. Yeah, I want to say 3. They don't know what the answer for 2 is. Okay, so what's an application of this theorem over there to strength? Well, it says that this example that Balico and others came up with, or this construction, is the only thing that can go wrong. So let me say this a bit more precisely. So there's a corollary of the theorem is that if you fix d and you fix r, then there exists an E such that for all n and for all f in k x1 up to xn d, in the closure of the strength at most r locus, well, there exists such an expression. So there exists an expression that says f is the limit for t to 0 of sum I is 1 up to r of fi, which now depends on the parameter t in the coefficients, times hi, which also depends on t, and where the exponent of T in the Fi and Hi are greater than or equal to E. Okay. So the point here is that, of course, if you fix the dimension, if you fix this n over here, then this is just a classical statement in algebraic geometry. If something is in the closure of the image of some map, then you can find such formal curves that when you substitute T is 0, well, when you substitute them in the map and then set T equal to 0, you get this expression. The point here is that this E here doesn't depend on the number of variables. Okay. Yeah, so not from this theorem, but we have results with Tammy and Amichai and Arthur that give a kind of bound in terms of R. So if you fix D, there's a formula for R which I forgot, but which gives an upper bound to the actual strength, given that the strength is that the border strength is at most R. But we don't actually have any bounds for this number E. We know that there is an algorithm that computes it, but it's not an algorithm that I'd like to implement. Okay, so I guess I'd like to say a little bit about the proof of this theorem. Oh yeah, sorry. Yeah, here too. So it's an expression like before. So homogeneous and the degrees add up to the degree of D. Yeah, thanks. It's a bit confused. Okay, so basically, so this corollary is not so difficult from the theorem. The point here is that that if you prove a theorem in the infinite dimensional setting, then it implies corresponding theorems in the finite dimensional settings with uniform bounds. And that's very much like one of the proofs that Ehrman, Sen, and Snowden gave for Stillman's conjecture, which is something about ideals generated by polynomials of a certain fixed degrees, but a varying number of variables. They also well, essentially, they show that conjecture holds in the infinite dimensional setting and then transport it back to the finite dimensional setting. Okay, so IDs in the proof. So one of the IDs is that we prove a different theorem, namely that if X is an irreducible, now this is the X over there, is an irreducible GL variety, and Z in X is an irreducible GL subvariety. Oh yeah, and also, and U sitting inside X without Z is GL stable and open. Yeah, closed. Sorry, what's that? Yeah, given by an ideal. Yeah. So a closed irreducible GL subvariety, and this is a GL stable open subset. Then there exists a curve C in X, and that meets both U and Z. And by curve, I just mean this is just, you know, maybe it's better to write it like this. This is just the spectrum of some finitely generated domain over K of crude dimension 1. Yeah, so it's just it's an ordinary curve. There's nothing GL stable about this. Yeah, and you can kind of imagine that well, once you have a curve, you can do formal completion at some point, and you get a Laurent series valued point out of that. The only thing is that from this you would get it inside X, and then you would still have to lift it via under phi to such a point in Y. But that involves techniques that we already knew. So this is really one of the new things in the paper. And so how do you do this? Well, you need to get a grip on a general GL variety, and not just on a general GL variety, but in fact on the pair of Z and X. Oh yeah, maybe I should have said we apply this to in the theorem over there. We apply this to Z equal to the orbit closure of X0 and U sitting inside the image of phi. Remember, there is this Chevalley theorem that says that the image of phi is constructible. So in particular, it contains a dense. Well, I guess I should have said dense here, otherwise it could be empty. It contains a dense GL stable subset of the image closure. So now, from earlier work, we knew the structure of GL varieties a little bit, but what we didn't know is the structure of these pairs of Z sitting inside X. So we use an earlier theorem that says given an irreducible, okay, I need to say this a little bit slower. Okay. Let me say it like this. So there's a notion of shifting, which is the following. GL is isomorphic to a subgroup of infinite of itself, consisting of all infinite by infinite matrices of this form. And so the map is just G, an infinite by infinite matrix in GL, goes to this matrix over here, where you have shifted G down by n spots. This is an n by n identity matrix. And so when you have a GL variety X, then you get a new GL variety which I call the shift over n of X, which is as a variety is just the same X, but now GL acts in this different way. Yeah, so it kind of fixes the first n coord, well, the E1 up to En in V. And we have a theorem that says that if X is irreducible, then there exists an N and an H in the coordinate ring of X. This is this reduced GL variety, GL algebra, such that H is invariant under this group. Let me call it Gn. It's the subgroup of GL consisting of such elements. So it's Gn invariant. And if you shift over n this variety x, and then you pass to the open subset where h is non-zero, yeah, then this still has an action of GL, because remember on this shifted thing, GL acts via Gn, and so it fixes this h. So this still has an action of GL, and this is isomorphic to B times A lambda, where B is some finite dimensional affine variety. And lambda is some tuple of partitions. Right, so every irreducible GL variety up to this shifting and this localization, it is of the form some finite dimensional variety times an infinite affine space. And so now in such varieties, it's easy to construct curves because, well, B is in fact an irreducible affine variety, so you can find many curves in their connecting points, and this is just an affine space, so it's also easy to find points in there. The problem is that we cannot use this directly in our setting because this H that we have over here might vanish on the subvariety Z. Remember, we wanted a curve that both contains points in this open subset U, which is not a problem, that will be hit by elements in here, but you also want to hit the set Z, and it might be that H vanishes on Z. And so what we do is we prove a version of this theorem for the pair x, z when Z has codimension 1. I can say if you want what that means, but not right now. Then the statement is precisely the same, except that the shift of Z over N with H inverted is C times A lambda, and C is a codimension 1 subvariety of B. And then in the general setting where Z may have infinite codimension in X, we do a kind of blow up to make it codimension 1. And so that's how we find this curve that we need in this theorem. Okay, I guess my time is more or less up, so I hope to have given you some insight into the wonderful geometry of GL varieties, and there's a lot more I could say about it, but let me stop here. Thanks.
Okay, thank you for the interesting talk. Are there other questions for the speaker?
Why you're interested in this? You didn't suddenly wake up and start with the definition.
Yeah, it's a good question. So I'm interested in applications of algebra and algebraic geometry, and in applications people study things like tensor rank and also slice rank of tensors, which is a version of strength where well, essentially you require one of the factors always to have to be a linear form, and so then when you study these notions, very often you have a notion that doesn't see the number, that doesn't see the dimension of the ambient vector, right? So you can study tensors of rank at most 4 in V tensor V, where V can have arbitrary dimension, and you might want to know, can I characterize these tensors by finitely many equations up to symmetry? And the answer is yes, due to this materiality.
For your last board, if you know the x, is it easy to say what lambda shows up when you do the shift?
Yeah. Well, actually, let me give you a small example of this, and maybe it gives a little bit of feeling for how this works. So It also ties in with why I chose rank 2 matrices over there. So rank 2 matrices, 3 by 3 determinants cut out rank 2 matrices. And so in that setting over there, what you would do is, well, you have your infinite by infinite matrix, and the H that you choose, oh, I think I wrote in Y. So it's Y11, Y12, Y21, and Y22. So the H that you would choose in this case is the 2 by 2 determinant of this matrix over here. And if you invert that, then you see that all the stuff over here is going to be determined by what is written over here, and what is written over here, and what's written over here, what's written over here, right? Because in the variety of rank 3 matrices, every coordinate over here times this determinant has some expression in this. And so in this case, the lambda that you would get is the tuple 1, 1, 1, 1. Right? Because that corresponds to this infinite vector and this infinite vector and this infinite vector and this. And so in general, when X is embedded in some A mu, then the lambda that you get is something that you get by doing a shift and then forgetting some of the terms in the shift.
Okay, any more questions?
It's more a philosophical question. How do you access the irreducible components without being able to access the components themselves? In the Noetherianity problem at the very beginning, you said the underlying reduced structure is Noetherian, but not we don't know whether it's true for the variety itself, GL-Varieties.
Irreducible component, you need to only close up that you don't need the scheme structure.
This is true, but
yield equal to the radical.
No, I mean I understand the definition, but what makes it possible if you look only at reduced ideals? And,
Okay. Wait. Where does this? Essentially, where does this theorem?
yeah, where is that so important to have?
I can say that by means of this. So the proof of this Noetherianity goes like this: that you do a kind of induction on. So you have some GL-Variety sitting inside an A lambda. You do a kind of induction on lambda. And what you take in your lambda, you take a partition of the largest size, and then there are two possibilities. Either those coordinates don't satisfy any equations compared to the rest, and then your variety is just kind of product, or they do, and in that case, you do this kind of shift. You show that, like in this example, that many of the coordinates on this biggest A lambda can be expressed in smaller ones on some open subset. And so then the thing is, this open subset lives in a lexicographically smaller A lambda, and so it's done by induction. And for the complement, you can look at the subvariety where the entire orbit of H is 0. And if you had chosen and so you do another kind of induction on the minimum degree of a polynomial that vanishes on your variety. And so you get your variety as a union of two things that are both Noetherian, but that doesn't tell you anything about whether the scheme itself would be Noetherian. That probably, I mean, if you knew by induction, probably this open part by induction you might assume is Noetherian as a scheme, but this operation of taking the union, I don't know how to. I think that's my point.
Thank you very much.
Okay. Any more questions? Okay, thank you again.